4 states, and in between the states we see the transitions. So for example, the state 0, 0 with a 0 at the input, meaning the dashed line. We reach again the 0 state with outputs being 0, 0, 0. So basically here we find the same information as in the trellis diagram. We are just a different visualization. And the trellis diagram has the benefit that we actually also see the temporal evolution more nicely. So basically each complete part of the trellis diagram contains the same information as the state diagram. Just looking at this bit duration by bit duration, we get some better insight in the temporal. Okay, this is also why we do the decoding based on the trellis diagram. So we want to find the sequence which most likely has been transmitted. And the Viterbi algorithm is so-called maximum likelihood sequence estimation. So we find the most likely sequence. So if we look at our example, so I assumed we transmitted this blue sequence here, valid sequence that is generated by this shift register from our example. But what we observe at the receiver is this red sequence here, where probably some errors are contained. And we will see actually how the Viterbi algorithm will deal with this kind of errors. And I think the approach is quite straightforward, the Viterbi algorithm. So it basically compares what did I receive, what are my observations, and what could have been possibly transmitted. So in the first time step, we know we start state 0. So our valid sequence, our encoded sequence can only start with 0, 0, 0 or with 1, 1, 1, depending on the bit that was encoded. If I observe a 0, 0, 1, first time step, something must have gone wrong. And now the question is, what is most likely? And there we know it is more likely that only one error occurs as if 2 errors occur. So if we just look at this first time step in the trellis diagram, we would say if we observe 0, 0, 1, well, probably 0, 0, 0 was transmitted and the last bit got corrupted. But it also could have been that 1, 1, 1 was transmitted and the first 2 bits were wrong, but it's more unlikely. And this is basically how we go through this trellis diagram by counting the number of different bits. So we get from the so-called branch matrix, like one branch of the trellis diagram, to the so-called path matrix, like the number of different bits for a whole path in the trellis. And this is basically how we continued, like so far, one bit being different. If this would be the valid way or the most likely way, here 3 bits would be different, which would result in a path matrix here of 4. Then we noticed at a certain point, some path will come together in the same points again. And there we just make something which is also straightforward. We just forget about the path where more bits are different as in the other path. Because they will probably, or they cannot be the most likely path. So this means we forget here about the higher numbers and trace further with the lower numbers. And this is how we continue all the way to the end. Yes, where we know we will end at the 0 state because of this so-called termination bits that we use. This makes sure that by inserting zeros at the input of our shift register, we will make sure that after 2 time steps in our example, the shift register will be filled with zeros, meaning we reach the 0 state again. This helps us to trace back more safely, because here we now only have to decide Was it the upper path or was it the lower path that we need to trace back? Whereas if we would not have the termination bits, just imagine the last two steps missing here, we would have to do the trace back from here, which would, actually, it would be unique here. We would, of course, also select the path with the lowest path matrix. We would do the trace back here from the 3. But it could also be that we had another 3 here, so the uncertainty for the traceback would be larger, as if we know that we have to trace back from a well-determined state here, like the 0 state at the end. So this is more safely, it reduces uncertainty if we have this termination bits. Okay, are there questions related to this Viterbi decoding? Yes. So let me repeat it also for the students in Kazan. There was the question, what if 2 errors occur in the first bit duration? So assuming here another error. So then, of course, this path will be more likely. We get the 1 here as matrix, the 2 here. Then we would have trace further from here. Again, here 2 would be different, here 3 would be different. So here we would already have like the equal number of different, but coming from here instead of coming from here. So it could actually be that it will fail in this case, because we are already quite close to the capabilities of this code, what we see here in the very close decision. If we had only 1 bit being different, we would get here a path with like a 1 at the end and with a quite high number up here. So this is already a very tough case from the number of errors. And you are right, probably 1 error more inserted anywhere here would make it fail. But of course, you could play it through, insert just another wrong bit and see how this basically evolves over the duration of the strategy. Some more questions? Yes, sure. So here's another good question. So the question was, how do we know when to add the termination bits? Well, this depends on the system that we are looking at. I will show you today also some practical examples how this was used in GSM and in UMTS. And there we have certain frame sizes depending on the information that we transmit. I think in GSM it was like 800 bits or so. And after this block, basically the termination bits are appended. So there's no rule that you have to say after each 10 bits we insert termination bits. Of course, this would help to reach a safe state after 10 bits, but of course it also introduces redundancy again, which we actually do not like so much. We would rather transmit more information bits. This is also why the latest version of this convolutional codes that have been used basically avoided the termination bits at all. So we speak about so-called tail biting convolutional codes, where we avoid these tail bits or termination bits. So there are also methods this can be done. What you see already from your engineering experience, you know, of course, this will be a trade-off. We get some uncertainty for the decoding, and the benefit is we have 2 additional information bits that we can transmit. Okay. So let's see some facts here. Functional codes. Okay, here's basically just a summary how this Viterbi algorithm is working. We explained this now in detail. I think this is not so difficult. Maybe one thing I forgot to mention, again, at the example with our Viterbi decoding. The Viterbi decoding also has another big advantage. It's very easy to incorporate soft information here in this decoding app. Just imagine we consider again an additive white Gaussian noise channel, like with a bipolar modulation scheme. So we send +1 and -1 at Gaussian noise. So we receive arbitrary values here. So do you have an idea how we would have to modify our metric in this case if we receive here real valued quantities in case we use an AWGN channel? Yes, exactly. So here we got the answer immediately. One student here, we just should use the Euclidean distance instead of the Hamming distance. So we would measure the Euclidean distance between what I received and here, for example, +1, +1, +1, measure the Euclidean distance, and here -1, -1, -1, measure the Euclidean distance to what we received. And then basically do the same with the Euclidean distance as what we did before with the distance. So it's very easy to modify this algorithm to a so-called soft output Viterbi. This is straightforward. Okay. So then there's another question that could be asked. How good are convolutional codes if we compare them with block codes, for example? So for the block codes, we know we can basically get an idea of how powerful they are. We provide the minimum Hamming distance. So in how many bits are two code words different in the worst case? How different are the two most similar code words? This is actually the question behind it, because it's most likely that we will get an error in the two most similar code words. So for convolutional codes, we have a similar measure, so-called free distance. So this is exactly similar to the block codes. It's the number of bits in which two different sequences are different. So again, if we look at our example, just to give you the idea of the meaning. This one. So look at this. This was the encoder. So the all zero sequence would be a valid sequence of our encoder. Then we would have the 1, 1, 1, 0, 0, 1, 0, 1, 1. This would be a valid sequence. So here we could already compare in how many bits is this sequence different here to our all zero sequence, or in how many bits is this sequence different. So similar as for our code words in the block codes, where we compare how many bits are different, we can do it here in the same way by asking how many bits are different between the various sequences. But of course, you see the problem. Theoretically, we could have here like infinite length sequences. So how to define a useful measure? And there we actually will get to know this so-called free distance, which basically is the number of bits being different in the sequence emerging at the all zero state, means starting here at the all zero state, and remerging at the zero state on the shortest way. How many bits are different this way as compared to the all zero sequence? Also notice here for the linear block codes, we stated that we get the minimum Hamming distance by finding the code word which is most similar to the all zero code word. So the code word with the lowest number of ones gave us there the minimum Hamming distance. And here we look for the sequence being most similar zero sequence. This is exactly what we need to do to determine this free distance. So let's get to this here. So here it's also written, free distance is defined by the path diverging and remerging to the zero path with the minimum weight. So we have a path here diverging from the zero path and remerging at the zero path, and its Hamming weight, so the number of ones here is 1, 2, 4, 5, 6. So we have 6 ones here. This will be the sequence being most similar to the all zero sequence. We have either 9 zeros or we have this sequence here with 6 ones. Of course, there are also other sequences emerging or diverging and remerging at the all zero sequence. For example, here this orange one, going back one time step further with the 8 bits being different from the all zero sequence. So this is why we cannot really use this free distance in exactly the same way as we use the minimum Hamming distance. So we could say if we have a free distance of 6 here, we could correct d min minus 1/2 and the floor of it bits within this sequence of 9 bits. But this is not how it's typically used. It's typically just used as a performance number of this convolutional codes. A convolutional code with a free distance of 8 will be better as one with just free distance being 6. Meaning the one with 8 contains more differently looking sequences. That's the main. Okay, and here we already have an example for the code with generators 577. So this was a famous one being used in GSM. It reached a free distance of 8. So you see our randomly chosen example, the 457, is not as good as the 577, because this would reach an even larger free distance. This is why you will find no application where a 4,5,7 code is used. If you would want a rate 1/3 convolutional code with memory 2, you would use the 577, which you would get from a table. Okay. Yes, actually here I copied the table with the optimal codes, so meaning reaching the maximum free distance for given parameters, where the parameters are the code rate and the memory. So how large is my memory shift register and how many redundant bits do I want to introduce? Rate 1/3 are already very strong codes. And for one information bit, I need to transmit 3 encoded bits. And here you see the typical example, like the rate 1/2 code with constraint length 3, memory 2, 3 bits, influencing our current bits, just reaches a free distance of 5. Whereas look at a larger one, this one here, rate 1/2, constraint length 4, meaning 5, meaning a memory of 4. So we have 4 bits in our shift register. This already reaches a free distance of 7. So meaning increasing the length of our register is to generate more different sequences. So this means we reach a larger free distance. So this means we can trade off here a better performance for the cost of an increased computational complexity. So I've shown you trellis diagrams for larger memories. It will start to get more complex then. But this was already like the evolution path from GSM to UMTS approximately. More powerful devices, increased free distance. Then here we have the stronger codes, like with rate 1/3. So adding more redundancy, of course, will help. So here with a constraint length of 3, we already reach a free distance of 8. So this code will be already more powerful as the rate 1/2 code up here. But it's no surprise as we transmit one more redundant. Invest more redundancy in order to get a more powerful. And here's some more that I used. Again, those are the optimal codes reaching the maximum free distance with this given parameters. And you will find these tables in the book. And I think I mentioned it at the beginning, those parameters have been found in computer search. So there's no like closed form algorithm that will give you the best set of generators. Okay. Yes, one question. Yes, yes. So let me repeat it for the students in Kazan as well. So here was the statement or the question. So the student here noticed that our 4,5,7 code from our example is a rate 1/3 code, and it reaches only the free distance of 6. And looking at the table, he noticed that we could actually reach this free distance also with a rate 1/2 code. For example, with if we increase the memory just by 1, so for a small increase in complexity, we would get the same performance or an even better performance with just a rate 1/2 code. So we would really save a lot of redundancy to be transmitted and get even a better performance just for an increased complexity. Yes, this is right. So of course it would be smart in our example not to use the 4,5,7 code, but instead go to a rate 1/2 code with a memory of 3, for example. Yes, very good. Okay, so let's see how this story here continues. So we get to our examples. I already have briefly shown this last time. So from the GSM system. So I already explained this. Now we have 3 different classes of bits. The ones who need to be protected very well, like location data or communication signaling between the mobile phone and the base station, like telling the base station that I'm now entering the corresponding cell. So this is the information which is here highly protected by a cyclic redundancy check and the convolutional coder afterwards. Then we have the class 1B data. This could be like internet data or probably also things like SMS data, where you actually want to avoid bits being wrong. So it could cause problems. It will show you wrong letters or wrong pictures, wrong sounds. So you would like to avoid this. And finally, we have class 2 data, the not so important data, which is not entering the convolutional code. And here, you're actually referring to your question before. You see the 4 termination bits get added. So this means obviously we have here code with memory 4, constraint length 5 that is used. Well, at the end we get the rate 1/2 code, get twice the number of bits out here, and they get multiplexed because at the end we need like a sequential stream of bits. We just need to know how to multiplex this together. So this is basically how things looked in GSM. It's like for 189 bits to be processed. After that, we append these 4 termination bits. Okay, here's some technical data, also just for interest. So the length of the voice samples, this is more like signals and system theory. How dense do you have to sample the voice? And how many bits do you use to quantize the voice? Or nowadays, maybe the more interesting questions even, which kind of codecs do you apply to compress your data? This is another question related to this. Okay, so see, is there something interesting for us? Yes, here the convolutional coder that was used, rate 1/2 coder, constraint length 5. We already have seen this on the diagram before, with generators being 23, 35. We would also find this in the table of Marcus, so the best possible for this size of memory. And this one will reach a free distance of 7. And we use terminated. To come up with a successor, so a following system for GSM, and this is why basically they were first to deploy UMTS. But at the end also UMTS made its way all around the world, so and became the dominant start 1000. At the part that is interesting for us from the coding point of view, so you see actually not really a lot happened there. So still convolutional codes were used in UMTS. Notice the large constraint length now, constraint length 9, meaning a memory 8, because this belongs to a larger generator. This requires larger generators. And see the free distance increased significantly. So again, we traded in a larger free distance for the price of increased computational complexity. But obviously also our mobile devices became more. This is basically a development step in terms of just the codes that have been used. Also, some new codes got standardized, robo codes. We will get to know them today. They are basically also just like a concatenation of convolutional codes. So also these ones were based on convolutional codes. So yeah, actually really roughly spoken, not really a lot of new things happening. Look here at the structure, also copied from the standard. We also had, again, like transport blocks containing the data. We had a cyclic redundancy check. We had 8 tail bits here, because this results from the constraint length. So again, terminated codes are being used. Yes, of course, the rate 1/2 coder will double the number of bits, so we get 540 bits here. So actually, yes. Then we have some radio frame segmentation. So this is the part where, at least for our lecture, just being interested in the error protection scheme, here starts the part which is not so interesting for us. And this is like the higher layers. I think Professor Seitz is dealing with this, or Professor Mitchell et al. In their lectures, where they higher layers of such a communication system. For us, basically, the story up to here is interesting. Okay. This is copied from the standard, and what you will also notice if you look up some standards, that of course things become more complicated. So already here, the document on the channel coding, multiplexing, is an 82-page document defining different sets of parameters, again for different kinds of channels. So we have data channels, we have signaling channels, we have channel state information channels. So we have a whole bunch of different channels containing different data where differently strong protections are applied. So it's a bigger story. It's just drawing one example out of this bigger story to show you that still convolutional codes were used there. Okay, let's see, the story continues. So here we go a bit further. LTE release 11, so this was around 2014, but also still up to 2019, so also still quite recent. There, I mentioned it already, so-called tail-biting convolutional codes were used. So there, we don't use the termination bits anymore. But besides this, you see again, the major difference is, at least here, okay, it's not really comparable with the first ones. But of course, again, the computational capabilities of our devices increased, so we can use, again, large generators. Here, as example, a rate 1/3 code, which reaches a free distance of 15. And here you see actually the encoder structure, also copied from the standard. So this is how you will find it if you look at UMT or LTE standard here. You will find this kind of drawing. Also here, notice generators provided in an octal form, as we learned it also in our lecture. And then this is the next part that we want to talk about, the turbo codes that have been standardized. But already notice the structure here. So we see again our registers here. The difference to what we did so far is that here we have a feedback. These registers. Feedback, some information to the input. This makes it a little bit more difficult to deal with, but the idea is still the same. So we have a shift register, and we link somehow previous bits and current bits together to generate the outputs. And for the turbo codes, we use 2 of those in parallel. And why it is like this, we will also get to know this on Thursday. But before we do this, we need to have an insight in how these encoders with feedback actually work. So I'm not sure how strong your background in signal processing is if you have treated digital filters in one of your elementary classes. You will know the so-called FIR, the finite impulse response filters. So this would correspond to something like up here, some measurements entering the register and being processed somehow with this. So this is nothing else but a digital filter. Just with the difference, we treat it like a binary way, zeros and ones. And this recursive structure here This would correspond to an IIR filter, infinite impulse response filter. Also this you should know from signal processing. You could enter here a measurement value at the input of this structure, and depending on the parameters, this could circle around here like forever. But have such a system with an infinite impulse response. And then depending on how far you got into this filter theory, you notice in order to get a specific filter response, you will need a fairly large finite impulse response filter, but you could also achieve this, the same impulse response, with a shorter infinite impulse response filter. So this is somehow more efficient in linking information of several bits together. So I could easily come up with such a structure where the input would influence the next 10 outputs. If I want to do this with a structure up here, I would need 10 delays to achieve this. So these recursive codes became more efficient in terms of how many delays do we need and how many bits can we link together. How many bits can we distribute our initial? This is the main idea behind introducing this feedback. So actually now, as I explain you this, I'm actually wondering why it took up to 2014 till these structures found their way in the standard. This is interesting for me, so I should do some research there. So what happened before? Have these recursive codes not been studied enough? I'm sure they have been known in 2000, but why they have been used? Maybe one idea that you could also have from your knowledge on signal processing, maybe you know it, what can be the problem with the infinite impulse response filters? Yes. Also here, one student commented, stability is always an issue with the feedback systems. So in infinite impulse response filters, if you have like a wrong feedback or you have selected your filter coefficients badly, it could be that the output gets larger and larger, amplifying by the feedbacks. So stability is typically an issue if you have recursive systems. Very good. Okay, and here a roadmap that I included, that you see the evolution also of this wireless standards. I think I also have an updated one in the new slide set, where we here see the release 16 going up here to 2020. After that, basically, the tail-biting convolutional codes are replaced by the polar codes, and the turbo codes are replaced by the low-density parity chain codes. So this is where we are now, using the LDPC codes and the polar codes from here. Okay, so here we have a general question in the chat. General question, is the encoding done the data bits at the transport layer were created at physical layer? Let's assume at DSP algorithm layer as well. It's a kind of difficult question for me to answer. So where is this actually done physically? So, well, it depends a bit how you separate the layers. Because typically you start, if you take a mobile phone and let's assume you do a phone call. Because you have your voice data being sampled to some binary values, and the binary values entering some source coder where you do Huffman encoding or smart compression like MP3 or any kind of compression. And after that, you would actually apply our encoder. Basically, right in between the source coder, where we have the bits that should be transmitted, and before the modulator. Modulator input would be the encoded bits. And this is why I would still consider this as physical layer. And the decoding in the same way, you would have the demodulation, and right after demodulation, you would do decoding. And after decoding, you would do like the block processing or the frame processing and separating the different data streams or signaling streams. So I would consider all what we do here as physical layer processing.
Okay.
This,
So I felt like the modulator or demodulator, I can assume it as physical layer. And let's say I got the data, like the example we have seen, speech encoding. Because of the pattern, we are using the sequence, maximum likelihood sequence. So once we decode that in my phone, let's say I'm hearing a song, in that case, the algorithm is working on application layer again. So once we got from the demodulator, so is this algorithm working on top of it, or demodulator itself the algorithm?
Still not sure if I got your question correctly.
Uh, I'm trying to say, like, the demodulator that we have embedded an algorithm inside it. So in that case, it might be a physical layer. But I'm not sure if I'm writing an algorithm on, like, let's say a Python program, something like that. So I'm assuming it as application layer, writing an algorithm. Like, I'm confused between physical and application layer.
Yes, so I think there it really depends a bit how you separate the different layers. Of course, also the demodulation and the decoding will be nowadays some software functionality. So we get more towards software-defined radio. So we have multiple band devices, basically, where you can actually adjust the whole receiver settings by software. So I would not say just because some functionalities are done by software, we don't consider this as physical layer. So, but well, of course, this could be discussed, but well, from my point of view, it is physical layer, although the functionalities are, of course, implemented in software.
Okay. Okay. Yeah. Thanks, sir.
Okay, and here actually is the updated slide to see how the story will continue. So with release 17, release 18, so which is currently worked at, talk about 5.5G, and actually 6G is now, let's say, under research. So we typically assume or consider from experience that it takes about 10 years for such a wireless standard to come from the research state up to the deployment state. So also the things that we employ now, like 5G systems, have been under research since 10 years approximately. So those are like time constants until when certain development, certain research reaches the state where like the worldwide community agrees on a common standard and says, hey, let us use it in such a way. Because that's one main requirement for a successful wireless standard, that in the best case, all over the world, the experts agree to this. Okay. So otherwise, if you would just develop one standard in your country, and the other one would use this one. So no matter how good your standard will be, it won't be successful. This always needs to be considered. But this is also why worldwide groups of researchers meet regularly and talk about state of the art in research and how this could be used in wireless standards. So, for example, the so-called Wireless World Research Forum is one of this forum, or experts from academia and industry come together and discuss what should be done in 6G, for example. And actually, we also contribute there. So I know that Professor Hart is regularly attending these meetings. Of course, this is also very important when it comes to how research actually works. So there he meets research bodies, basically working on the same projects, on the same topics. And this is also the place where they form groups of researchers and apply for research grants, research projects. So this is basically where ideas are generated. So very important. Okay. But these are just some side notes beside all the theory that you need to study. So we have sometimes the convolutional codes are also described by polynomials. So if you see this somewhere in a book or a publication, polynomial description, just for completeness, I also explained to you how to interpret this and how to get the connection to our octal description of generators. So don't be confused if you see other descriptions of what we did here. So that typically you will find an easy way to get back and forth how we studied it. So we did it this way with the octal numbers, because this is how you will find it in the wireless standards and how you will communication Bible by Proakis. Okay, and also for completeness, the cyclic redundancy check, because I mentioned it several times. Here you will find an example how the cyclic redundancy check is working. It's basically a polynomial division. You describe the generators by the polynomials, and you divide your message, also described by a polynomial, by such a generator, or by such a generator. And after this polynomial division, you get like a remaining part, like a rest, and this is basically just what you append to the data bits. And at the receiver, you just repeat this polynomial division, and if you get a different rest here, remainder, you know something went wrong. So it's a very simple error detection scheme. You cannot correct errors with this, but you can figure out if something went wrong. So error detection, not detection. But you have seen it, for example, in GSM. This is used additionally. Okay, just example. And here, finally, the example for okay, so far to the functional codes. Are questions? Otherwise, we want to start today with the recursive convolutional codes. Recursive convolutional codes. So, and we look at an even more specific class, recursive systematic codes. Just write down they are used. Yes. Probocodes. So this is always a bit my focus, the mobile communications applications in mind, looking what is going on there. Because typically that's also the most interesting application, because there we are facing the most difficult channel conditions. Just imagine you walk around with, go to the basement. Channel conditions rapidly changing a lot. Driving at 300 kilometers per hour in a train. By severe Doppler shifts, and also your system needs to cope with this. Of course, there are also channel conditions which would be even more interesting if you think about like deep space communication. Of course, this would be also interesting, but it's not, it has not such a broad focus as mobile communications. Okay, so let's see how these codes work. Coming up with an example. Let's consider a RAID 1/2 code. Structure looking like this. So notice we will have the feedback, so we need an addition here before we enter our shift register. Zooming here again, we have our delays by 1 bit duration. And just in our example, let us define some feedback. So I will feedback last bit. This one, it should go back to the input. Also, I also will have like forward path. So I just want to use the first bit plus the last one. This should be my output. It's AR2, it's actually the second out. The first output, as we are talking about systematic codes, will be the same as the input. Directly observe first output. Now, how this feedback looks like. So which bits in the shift register are fed back to the input? Again, we will need some kind of generator describing these connections. And we will have a generator for this forward path describing these connections. So we have a so-called feedback generator. We will always have the 1 at the first position, because in any case, I need this first connection. That's the at these places, so I get 2. Or again, in octal form, this would be 1 plus 2 plus 4. It's 7 octals. Forward path. Narrator. One. So this will be the feed generator, and this 1 is 4, 5. Highlight this. And here for this first bit, we have the systematic. Remember the systematic block code. Puts in R. So at time step R will be the input value. Now notice what we get in the states now is not just the delayed bits of the input. So here we will not have UR minus. Adding the feedback. Then here we will have the delayed version, XR minus 1, and here we will get XR minus 2. Also should label the feedback somehow. I called it X1. Just notice this is not really so smart. So if we would consider and now let us think about how this thing works now. As I said, it's a little bit more difficult. For we will need the input bit. Minus 1, XR minus 2. x1. We will need like the register input xr. Any columns, you will see it more easily. But for the start, let us better draw more columns to make it more clear. So we have input, we have state, we have feedback, we have the register input. Next would be interesting, the following state. State. Well, and finally, of course, we are also interested in the encoder outputs, no? AR1 and see how this works. Yeah, if you have no better idea, we start. Look at the consequences. Of course, the 0 at the input has right away the consequence the first output bit will be a 0. This is the most easy question to answer here. So x1 is 0. XR, the register input, 0 coming from will be also 0. And think about the following. Then here, and this 0, we will see it over. So the following state will be 0, 0. And the second output, XR being 0 and XR minus 2, 0, meaning AR2 will be 0 as well. We are interested in all possible combinations that could occur here. So next, assume the state 0, 0, current input a 1. Input a 1, meaning first output being a 1 as well. State 0. Zero from the feedback plus a 1 from the input will be a 1 at the register input. And again, straightforward, following state, the XR will move here, the XR minus 1 will move here. So follow. One, 0 is 1. Now maybe it's a good practice for you. So I give you like 5 minutes, just think about this. How this turns into output bits and the following states. just take a couple of minutes to solve this. Thank you. Students are done, so yeah, or solve it and see if you got the same. So let's see, 0, 1 in the state. So this means the feedback is a 1 coming from the last bit here. Register input is the 0 plus the 1 back, so it's a 1. XR being a 1, meaning the following state would be 1, 0. Student from Kazan posted the sound. Mistake. 0. And the output will be the systematic bit, the 0 from the state, last one here. And for this one, 0, 1 in the state, the feedback will be again a 1. The register input will be the 1 plus the 1 from the input, a 0. The following state will be this 0 and 0, 1 from 0, 0. And the outputs will be the systematic bit, the 1 from the input, the 1 from XR plus XR minus 2 will be 1. This one again, this looks a bit strange. XR is 1, XR minus 2 is 1, sum is 0. So this needs to be a 0. So did anybody get the same? One comment here. So here is a good question actually. The student asked here, do we consider x1 at the current state or the previous state or the next state? I know that this often confuses students if they think in this kind of registers, at which time step do we consider? And just take it as one snapshot in time. So we have values here and here. We have a value at the input, and these values here and here directly determine this one. So we have the x1 at the same time as these values in the state and the input. So this means xr at the same time will be determined by these two guys, this one and x1. So everything at the same time. Okay, and basically we could continue like this for all combinations, and with this actually make up the trellis diagram from here. Yes. So here's again the question about the timing. So the AR2, we consider this at the same time step. So looking at the values, determining the feedback at the same time, this will result in this XR. At the same time, this will result in the AR2. So the AR2 will be in the same time step. And of course, then if we propagate over time, of course, in the next time step, we would have to consider the updated state and work from this on. This is now the table, is now not the temporal evolution, it's just listing the number of combinations that can occur. Okay, and from here we could draw, for example, the trellis diagram. We could also do the Viterbi decoding. This is all valid what we do. Just one thing gets a little bit more difficult. It's the termination. So let me explain it first. You will see it right away. So for the non-recursive codes, we have seen straightforward if we insert zeros after 2 or 3 time steps, our shift register will be filled with zeros. Here it's not so easy anymore. So it can be that I insert zeros here, but if I get a 1 from the feedback, this 1 could circle around here. Just inserting zeros here will not necessarily force my state back to 0. There could be a 1 circling around. Need to come up with a more smart idea related to the termination. So maybe you actually get the idea when I explain you what we need to achieve. So we need to achieve zeros here at the input of the register. If I can make it to get 2 zeros here in a sequence, I will have 2 time steps later, I will have the 0 state. So now basically the question is, how can I choose the inputs UR such that I will always get a 0 here? You see this? I want the output of this sum always to be 0. Yes, yes. Actually here, I think at least we got the correct answer. So the student here said, we need to make sure that both values entering here this addition are the same, because 1 and 1 will be 0, and 0 and 0 will be 0. So, and with this thinking, he actually got the solution. So in order to terminate the code, we need to make sure, let's draw this in red. We need to make sure that the input is the same as our termination, our feedback. So we would have flip a switch here. Then probably you notice that this will exactly do what you proposed. So if the feedback is a 1, we get a 1 here in our addition, and we get a 1 around here in our addition, which will generate the 0 here. Time steps later, the register will be filled with zeros, we reach the 0 state. Let's write this. Maybe it was a bit too quick. Actually, I can also show you how this looks in this diagram. We don't draw this now. This is actually the trellis diagram corresponding to our example. And now if I do the termination as we proposed it, you see, for example, from the state 1, 1, I will reach the 0 state with a 0 at the input and a 1 at the input. This will make my shift register input 0 and at the end reaching the 0 state. Here from the state 0, 1, I will need a 1 to go to the 0 state. So here the termination is not only by inserting zeros, it's more difficult. And here it's written again. It's generated by switching the input to the feed. Actually, here you see this again. Example with a table. So I always recommend to make like large tables. Better write down more values as not enough values to keep the overview what is going on. Here, example actually how the termination works. So actually start with slides that, unless there are questions now related. Then I can show you all this will look on Thursday. Just open the slides. Actually, these are the ones that are used in UMTS. So you see we have a generator with 1, 5 or 13 generator. Forward, this means we use the first, the second, and fourth bit for the feedback and for the feed forward. And we have the feedback generator of 13, the first one, not the second, but the third. Again, also for the UMTS turbo code, of course, recursive systematic encoders are defined by using these generators, as we've learned it. And actually here, grade 1/3 encoder is defined. We have, again, the systematic bit, which we will need in our iterative decoder. So we will see why this is important. And we have 2 times encoded versions of this input bit, once encoded by this first encoder and once encoded by the second encoder here, using just interleaved data. Yeah, we will talk about this on Thursday. So this interleaver basically just reorders position of bits, so it does some temporal mixing of the bits. So this means our bit UR will have different neighboring bits down here as compared to up here. So this means the whole idea of this interleaver and these 2 encoders is to get here statistically independent encoded versions of the same bit, because I encoded with different neighboring bits. And you know from our theory here how this convolutional or recursive codes work, they somehow link the information between neighboring bits together, extract this at the decoder. And here basically different bits contain the information on bit UR as up here. And this is what we want to use then later on in the decoder stage. We decode the bit here from AR2, and we have a second decoder decoding the bit AR3 with statistically independent information, and we will use the information that decoder 1 generates as a priori information for decoder 2, which will decode this independent. And thereby we can basically increase the information by iterating between these 2 decoders. That's already the whole story, and we will talk about this in more detail on Thursday, but you could already get the main idea. Statistically independent versions of the same bit here, the encoded bit, and I want to benefit from the statistically dependence in the iterative decoder. Okay, it's fine for today to get so far. And actually, again, these are pictures from standard. No, I think I've drawn them, but you will find them directly in the same way in the standard. We use here parallel concatenated convolutional codes. Of course, you could also have the idea of linking 2 convolutional codes after each other, like a serial concatenation. But there again, I included this type of codes in the lecture because those are the ones being used in mobile communications. And yeah, of course, there's a reason for this. They are slightly superior to serial concatenations. You could also concatenate block codes in any kind, serial or parallel, but you will get the best result by concatenating the best possible convolutional codes, which are these recursive structures, and from the parallel. Okay, are there questions? So then, thank you for your attention, and we will meet again on Thursday for our last lecture, where we get some more insight in these turbo codes. Okay, so thank you, and this afternoon.